we've heard, well, the moon's a distraction from Elon Musk, but unfortunately, Mr. Musk may be a brilliant man, but he doesn't understand space exploration. We cannot do humans to Mars without the moon. And if we don't learn to live and work productively off planet in our own back garden, Mars is a one and done at best. Right now, I think if we stampede to Mars with humans, there's no point in bringing them back because they're just not going to be alive. So we need to understand the environment. We need to know that humans can adapt to the environment outside of Earth's magnetosphere.
It is a fascinating time because I think that you have been involved with NASA for a really long time, that you are aware of where they were doing things in a quickly and when they were kind of stuck, and now with the privatization and the collaboration with private institutions and private companies kind of opened up again in a different way than it was. So I'm excited to hear about your perspective on how the history transitioned to that.
Yeah, the history is interesting because when I was a postdoc, it was the first time that the United States was going to go back to the moon since Apollo with the Strategic Exploration Initiative under George Bush Sr. And that we had a administration change, and that got cancelled. And then we had George Bush Jr. come in with the Constellation program and the vision for space exploration, and we were going great. And then we had an administration change, and it got cancelled. And then we had President Trump come in 2017 and gave us Space Policy Directive 1, and we were going back to the moon. Then we had an administration change, but the space policy didn't. And that is the first time since Apollo that the United States has kept a space policy after an administration change. And this is what's giving it a lot of traction, so that we have a destination that is not changed, so progress can be made, because space exploration, especially human space exploration, is a multi-decadal endeavor. And if you can't keep the focus over multiple decades, you end up going nowhere. And that's exactly what happened with the United States. Yes, we had International Space Station, and we were sending astronauts there, and we still send astronauts there. But beyond that, to actually relive the glory days of Apollo, we couldn't do it. So now we have a chance to do that because focus has been maintained, and not only has it allowed international partners to become involved, but the commercial side is now ready and willing and able to contribute to that endeavor, and that makes all the difference.
This was something that I wanted to speak to you about. This aspect of the continuation of the space policy, and how different it feels like throughout the years, whenever anyone hears about what NASA's doing, for us that we're not involved as you are, it looks to us that it's kind of there is not one direction that anyone can talk about and say, I know what NASA's going to be doing for the next 10 years. It feels like there were many projects, maybe they're interconnected from behind the scenes, but to us, it feels like every administration, the NASA director comes in, there is a new thing that they think, or at least to us, it feels like they are introducing this new program because they think this is the best, but there is not one single master plan, even if it changed throughout the years, single master plan that you can say, okay, now we are in step 3 of this master plan to get to where we want. And you need that to get a goal at the end.
And that's what's happening now. Now, the nuances of that master plan may change a little bit, and we've heard, well, the moon's a distraction from Elon Musk, but unfortunately, Mr. Musk may be a brilliant man, but he doesn't understand space exploration. We cannot do humans to Mars without the moon. And if we don't learn to live and work productively off planet in our own back garden, Mars is a one and done at best. Right now, I think if we stampede to Mars with humans, there's no point in bringing them back because they're just not going to be alive. So we need to understand the environment. We need to know that humans can adapt to the environment outside of Earth's magnetosphere. That can then allow them to transfer from the Earth Moon system to Mars, because having a database of humans, how humans react to 1/6 gravity, could be very enabling for a Mars transfer vehicle. Is 1/6 gravity enough to actually stop your skeleton from being resorbed? And if that's the case, then your requirements for a Mars transfer vehicle, it could be more manageable. I'm not an engineer, I'm a geologist, but I mean 1/6G versus 1G could be something to be very advantageous that would allow the humans to be productive when they actually get to Mars. But we need the data, and as Kraft Ericke, the German-American rocket engineer, said, and I'm paraphrasing, if God intended humans to be a spacefaring species, he'd have given them a moon. and well, we've got a moon, so we need to use it to do many things. Part of the many things is humans to Mars. The other part is to make life better down here through economic growth, through new technology developments, through new breakthroughs in mineral processing that doesn't involve water. Because if we're going to use the resources of the moon, we're not going to be able to use water to beneficiate the product. So those new technologies could spin back to Earth and make mining down here much more environmentally friendly. And so this is the value of the moon. It's not just to go out further, but it's also to make life better down here.
Since we kind of started in the middle of a conversation, I would like to speak about yourself. So you're professor of planetary geology at Notre Dame, chair of NASA's Lunar Exploration Analysis.
Used to be.
From 2006 to 2010, and then again from 2015 to 2018. So you have been involved in what NASA defines as their next lunar exploration endeavor. And you're currently a member of the National Academics Committee on Astrobiology and Planetary Science, and your career also involved a lot of involvement within the ocean drilling as well.
That's correct. Yep.
So that feels like it's a 360 on everything that you need to know. Like you have the practical experience, you have the advisory experience, the research and the academics, and now you have launched a new initiative, which is the Lunar Exploration Prospecting Campaign.
Yep, that's correct. Yep.
Which we will talk about.
Okay.
But before we get there, I remembered one thing in Marshall's, I don't know if you're familiar with the Millennial Project, colonizing the galaxy in 8 easy steps by...
Yeah, I'm familiar with it, but it's been a while, so...
So in step 3, the Avalon, Savage talks about the moon in particular. And the way that he talks about the moon really aligns with how your vision is going to be. So it's kind of feels like what you're doing is kind of a manifestation of a cool visionary project. So please tell us about this and how you came about to where you are today.
Um, wow. Okay. Um, let's see. So I born and raised in the UK, but in England. Did my undergraduate and PhD work in England, and then got a postdoctoral research associateship that I never applied for. Part of which was to work on Apollo samples. So I thought, 2 years in America, that'll be fun. And the reason I got it was because uh, Larry Taylor was his name, needed a postdoc quickly, and I came in second at Arizona, so he got my CV from them. And so I came to America thinking, 2 years in America, then I'll go home, and that was 1986. And I just fell in love with the moon. I worked just Apollo samples. What's not to love? You know, you actually can go there and see them and touch them through a glove box and analyze them and investigate the mysteries that the moon has through actual samples that were collected in situ by astronauts. So that sort of got me going in terms of samples. But then I found over the years that I need to understand engineering. If I want to do robotic sample return, I need to understand how that can be done with robots. I need to understand rocketry. I need to understand policy and politics. I need to understand business if we're going to get the commercial aspects involved. And I need to be able to speak in a way that our elected officials and the general public will understand, because I can get caught up in geology and I can tell you all about the anorthosites on the moon, but everybody's going to go to sleep. So what I want to talk about when I talk about the moon to the general public, I want to talk about the reason we go to the moon, and that's to make life better down here. It's no other reason. Everything else is secondary. That's the whole point of space exploration, is to make life better on Earth. And if you look at Apollo, which was done to beat the Soviet Union to the moon, and you look at the economic benefits, the unforeseen economic benefits, and I do this. All right. Thank you, Apollo. Miniaturization of electronics. Do you see where it led, Apollo? How many billions have been made, or trillions that have been made over miniaturization of electronics? Computers and computing power. You know, the computer, this is vastly superior to Apollo 11's computer. All right, but yet we had humans in the loop that could actually not land in a boulder field and land, collect samples that are still being analyzed today, and return them safely to Earth. So human exploration becomes a manifest of it's a multidisciplinary topic, but it always comes back to the why do we go to the moon? And when I was chair of League the first time, we put together the United States Lunar Exploration Roadmap. And if you do wade through that, it took 4 years to put together. And if you do wade through that and then you read our space policy, you'll see a lot of parallels. So this is something that was community led. NASA requested it through the NASA Advisory Council, and it is now manifest in our space policy. Because the whole point, there was a couple of points to the roadmap. It was to understand how to live and work productively off planet so we can go elsewhere in the solar system and do that safely, and to keep doing it. And sustainability is a way not only to keep doing human space exploration, but to give the return on the taxpayer investment. And that's the big thing for maintaining a cadence of human exploration missions.
So before we get into, I'm really interested in hearing what the overall overview of the roadmap. What are the steps that can be identified as a general overview in order to make that happen?
Robotic exploration that enables human exploration is number one. But in doing so, you do an awful lot of science. So there's three themes: science. There's also learning to live and work productively off planet, so it's feed forward to other destinations. And then the third underpinning is sustainability, and that's commercial participation. It's in situ resource utilization. It's the return on investment through job growth. It's the return on investment through creating an ecosystem that is commercially driven. So the issue that I find now with NASA's Artemis architecture is that it is not developing a transition to commercial lunar operations so that NASA can afford to send humans to Mars. And that's what needs to be done. We don't want to abandon everything that the taxpayer has or will put up on the moon in order to go on to Mars, because that's a loss. So it needs to be maintained, and we need to set up an ecosystem that is commercially driven so that commerce can come in, make a profit, use the infrastructure that's been set up so that NASA can not withdraw completely from the moon, because it's a great training ground, but can dial back the money that's going to it so it can focus on sending humans to Mars at a regular cadence.
It sounds like what you're saying, which makes total sense, is that before we get to Mars, we need to make sure that the moon is a stepping stone. So
No,
how
no,
do
no,
you...
no, no. We don't use that term stepping stone.
Okay.
How do you make a stepping stone sustainable? You keep stepping on it. No, you step on it, then you leave it. It's. I hate that term. I
Okay.
break out in a rash when that happens. So, because I've heard it said by NASA officials, the moon is a stepping stone to Mars. Well, you're never going to get commercial involvement, because a stepping stone means you have a temporary use for the moon. That's not going to encourage commercial participation and investment, which requires a long-term commitment. So the language is really important. So, for example, 2020, the Artemis rollout documents came out, and they kept using the term sustained and sustainable, and it was really good. Until I asked a question of NASA officials: what is your definition of sustainable? And that's where I realized that words mean everything. So I also then asked, how do you make a stepping stone sustainable? Because the way you are articulating NASA's commitment to the moon is complete opposite to what you're saying about sustainability on the moon. A stepping stone is not sustainable. It's something to be used to go somewhere else. And so that narrative had to be gotten rid of, because you're never going to achieve commercial participation at the extent that it's going to be needed, because there's no long-term commitment.
Yeah, I guess you're absolutely right. Actually, my understanding of having the moon as a, even though I use the word stepping stone, is what you're saying. Is that how
Mm-hmm.
can we go to Mars before we even learn how to do it sustainably on our closest ever um,
Yeah,
potential?
our nearest neighbor. Yeah, and I agree with you on that. But you see, if we only go to the moon to learn how to go to Mars, we miss a big opportunity for job growth and setting up an ecosystem and having, as it clearly states in the United States space policy, a permanent human presence on the moon. And you won't have that. But that's what our space policy says the aim is: a permanent human presence on the moon. And you, if we don't set that up right at the moon, that we develop that sustainability mindset such that we do get a return on investment, how are we going to do that at Mars? Mars will be flags and footprints, one and done, and that will be it. And I don't want that to happen. So we have to get it right at the moon, and we're not going to abandon the moon. The moon will become will be brought into our economic sphere of influence, because that is a new sector of the world economy that is ready for growth. And if we can set it up such that we can make it grow, and governments are there to enable that, we set up a blueprint that we do the same on Mars. Now we've got much further away and the environment's very different. I've heard all the arguments. The environment on Mars is exactly the same to the environment on the moon as far as humans are concerned. It'll kill you. It's exactly the same. They're both toxic to humans. So we need to learn to live and work in that toxic environment close to home before we go millions of miles away. And if we don't do that, we're just going to be in the business of killing people, and I don't think that's the way we should do things.
So how do you see the best way to get there, to get to a sustainable or sustained continued presence that is thriving on the moon? Is it like, what do you feel about the Lunar Gateway? Is it one step before we actually have presence, or do you think that we should aim for the presence directly? How is it?
Okay. I'm trying to be diplomatic here. The gateway is probably the way we're going to do humans to Mars. I think there will be an orbital station around Mars so that 6 to 8 months of space travel doesn't end with now we've got to land. We've got to sort of get used to it, and we've got to try and understand what the dust storms are doing. We've got to understand many things in terms to get humans on the ground there. But the reason we have Gateway is that the Orion spacecraft on the Space Launch System was designed to dock with an asteroid. It was not designed to go into a gravity well. So Orion, if we go into the moon, cannot get to low lunar orbit. So we cannot do Apollo. So now we have Gateway. Or we could redesign the upper stage of the Orion spacecraft to have a bit more guts to it. But they've chosen to give us a Gateway because this is the way we're going to do it at Mars. And I sort of buy that. But now you've got a human landing system. Now we need another piece of the puzzle, because now we've got to get the humans to and from Gateway. And we have SpaceX Starship, and we have Blue Origin's Blue Moon. So if that's good, but if you've seen the size of Starship, Starship takes off from this planet. It has to undergo multiple in-orbit refuelings to be able to go to the moon and then come back again. For Artemis 3, there is no Gateway. So we will have the Starship dock with Orion in lunar orbit and then go to the moon, then launch from the moon, dock with Orion, and then come back to Earth. Okay, all well and good. But if we're going to go to the South Pole, there's not much flat ground at the South Pole. And Starship is a rather tall rocket. And not only is flat ground at a premium, will it actually be able to take off safely? Because it's Starship, the first fully integrated test of Starship, destroyed a custom-built launch pad and knocked out 7 Raptor engines, and that spacecraft started to spin uncontrollably and they had to destroy it. Now it's going to launch from unconsolidated regolith on the moon, assuming that it doesn't fall over once it lands. But we haven't thought this through in terms of keeping the astronauts safe. And we really need, urgently, a launch pad, landing and launch pad construction that needs to be looked at in very, very minute detail. Because these are human lives that are going to be on Artemis 3, and would really like. I'm sure they'd really like to get back to Earth. Now, same thing has happened with Starship goes to Mars. If it's going to land on the surface of Mars and then take off again, even more in orbit refuelings before it gets to Mars, comes back again. So I think we have an issue in the architecture that is people are either not addressing or they've ignored, and it's something that really is, I think, mission critical to think about now, rather than have a decadal inquiry into why we lost the first Americans back to the moon since 1972. And to me, that's something that needs to be really thought through. So thinking through the details is really important, and understanding what are the milestones, as we go back to the moon, this time to stay, is really, I think, critical. And it not everybody can think of these things, and it's, I'm an academic, so I'm going to criticize when I see a hole, but I like to think of it as constructive criticism because of the work and my experience in putting together these architectures, and also my experience that I've gained. This is a geologist speaking, but I've gained a bit more understanding of the intricacies of getting to and from the moon. So to me, I think that is something that we really need to think through. And it's not as if I've given my written input to the Artemis architecture definition team, and don't know what happened to it, but I didn't see it in this latest iteration. So you've gone very quiet.
Oh, sorry.
There you go.
Yeah,
You were muted. Yeah.
It sounds like from what you're saying is that once they have to contend with those real questions about what it means to actually have human life on the moon, then they would have to probably reach the conclusion that maybe there will be machinery first or robots first. But then even when they reach this conclusion, then the lunar environment with the characteristics of the regolith and the machinery, it also hasn't been tested. Like, it also needs to be kind of well thought of what's going to happen if the machinery, and please correct me if I'm wrong, but what will happen if the regolith got stuck in the robot while it's doing whatever it needs to do. It's a very big question, and you're right. Like, it's something that is going to be in this master plan in order to get to where we want to be. Right?
I absolutely agree. So you have to test. You have to test down here, which is ongoing. But in order to understand the environment you're going to be working in, you need to go there, and you actually have tech demonstrations on the lunar surface. This is why the Commercial Lunar Payload Services program is very important for exploration, but it's in the Science Mission Directorate. So why? Because NASA's very stovepiped, and it's doing science. It's not doing exploration. Technical demonstrations, we don't do that. It's like prospecting for resources. Science Mission Directorate doesn't do prospecting. So I've asked the question, who at NASA does prospecting? And nobody does. So that leads us into our later topic, but this is the problem we have with the stovepiped agency. It's not a one NASA. It really isn't. It's a NASA is made up of very stovepiped mission directorates that do their thing, and they will not do anything to blur those boundaries because it all comes down to budget.
Actually, I based on what you're saying, I'm thinking that, do you think that now the involvement of the private sector within NASA's or the governmental space agencies in general would force NASA to speed up its mission and transition from a science to exploration. Because if the market is able to find some justification why that goal should be pursued, do you think that it's going to help in making NASA have more agency?
I think the way to do that is to take the commercial lunar payload services out of the Science Mission Directorate and move it above the directorates so that all the directorates can take advantage of it. Because Space Technology Mission Directorate's got technical demonstrations they want to run, but they don't have the budget. ESDMD has demonstrations that they could do in terms of how to set up infrastructure, geotechnical properties of lunar regolith, fundamental things like that that would inform construction projects. So, you know, if that would be my druthers, but stuck in science with the narrow definition that lunar science has, is I think it's making the commercials come to that because they're getting paid. Yes, they can sell other excess payload capacity on their landers. That's great, but it is not driving exploration. And to think that the commercials are going to start driving exploration, right now that is not going to happen. So it is to change the paradigm, and I keep hearing CLIPS 2.0. Well, 2.0, they keep hearing about survive the night, which is great. But surviving the night is, we were operating during the lunar night with the experiments that Apollo left on the surface. And now we're talking about surviving. We've regressed. So it's a capability that we need to be able to operate. And I was very pleased with Nikki Fox, the Associate Administrator for the Science Mission Directorate, today on a congressional hearing I was listening to, because she corrected one of the committee members to talk about survive the night. She says, no, we want to operate during the night, not just survive. And yes, well done. Well done, because that's right. And so NASA can drive the evolution of the commercials. All right, and that's one way to do it. But having exploration and space technology also be a partner in CLIPS on an equal footing would allow more opportunities for commercial rather than just science.
And speaking of commercial, and to tie it back to an earlier point you made about how important vocabulary and semantics is, and you made the distinction between a resource and a reserve.
Yep.
And how it's important to distinguish between the two.
Yep.
Tell us more about this, please. And what is it in the moon that we're most interested in?
Wow.
That could maybe open the potential to drive this further.
So this is a 3-hour podcast, right? So okay. Well, I put on my geology hat to cover up the gleam off my forehead. Resource is something that we know exists, and we know its potential to be a resource to support operations where we are. All right, that's a resource in the broadest sense. So it's a concentration of a metal, it's a concentration of a volatile, and so you could use it for water to not only life support for humans, but also for rocket fuel, or you can use the metals that are up there to create structures. So we have those resources, but a reserve is a subset of a resource. This is where we now know that how much is there. We know the variability of that particular resource. We know the concentration. We know the impurities that are in there, and we know quantitatively how much is there. And we can extract it legally and economically. i.e. we can make a profit. And that's the difference. That's a reserve versus a resource, which is a very nebulous. Yes, there's water ice in the poles at the moon. We estimate there could be billions of tons of water ice, but that's a high risk estimation. We need ground truth. We need to get to the point where we can actually understand all those levels. Can we extractability, accessibility? Can we actually get to where that is? Can we actually get it out of the ground? Can we actually refine it in situ? Can we store the products? Can we use the products? And that requires prospecting, and prospecting is not a mission, it's a campaign. And if we've got to think of it in that campaign of missions category, such that we get the data to drive down the risk of sending surface assets to a particular location to get ground truth. We have a high probability of success if we send very expensive surface assets to a given location. So that is something that resources can form the underpinnings of a cislunar economy if we can prove their reserve potential.
NASA talks about resources. What do they mean? What are
Say again? Say again, you broke.
Oh, I mean, when NASA speaks, when we hear resources, it's always talked about in a vague term. Like, what are the resources? What are we mining for? What is it there?
Again, NASA's documents use the term resources when they actually mean reserves, because they talk about resources underpinning a vibrant cislunar economy. Resources won't do that. Reserves will. All right, big distinction. So understanding reserve potential is important. But the resources are those that can be used in situ to support humans on the moon. So the basic thing is power, solar power. That's a resource. We can put up solar panels, and as long as we have sunlight, we have power. The other thing I talked about is water. We know from the L-Cross mission, we've got our 1 point of ground truth, that there was about 5.5% water in Cabeus Crater, along with a lot of other nasties that told us, and our 1 point of ground truth tells us that we have to refine the water on the surface of the moon in order to make it palatable and for use as rocket fuel. And you can break it down to hydrogen and oxygen. So that's what we know now. We don't know if Cabeus is representative of every permanently shadowed crater at the poles that contains water ice. We don't know that. So we need to get ground truth from multiple locations, hence a campaign. Other things that people have looked at in terms of resources is regolith. All right, now we're going to mine the regolith. Polar volatiles are probably in the regolith. Regolith contains a lot of metals that can be refined to create structures. Titanium in the high titanium basalt maria, but you've also got aluminum in, or aluminium, I should say, at the poles, because you have a lot of the mineral plagioclase, which is aluminium rich. So again, aluminium's a lightweight structure, but on 6G, it needs to be strong to withstand micrometeoroid bombardment. Regolith is also important because you are going to need to cover your habitat with at least 2 meters of regolith, and maybe a meter of water to stop ionizing radiation. But you need at least 2 meters of regolith to protect the humans from micrometeorites, radiation, both primary and secondary, because as galactic cosmic rays hit the lunar regolith, they actually create secondary radiation from the materials that are in the regolith, and solar flares. The other thing you need to bury it for is thermal. We know that at the Apollo equatorial sites, there's about a 300 degrees Celsius temperature swing between lunar night and lunar day. Having a habitat exposed to that is going to be an engineering nightmare for creating a constant environment. So we bury it, and you're not subject to those thermal swings anymore because the regolith is a really good insulator. So we talk about human permanence, they're going to have to be in habitats that are at least covered by 2 meters of regolith, or they're going to have to be in lava tubes that we now know exist in the Maria. That's not at the poles; it's away from the water. So, well, but maybe the lava, we don't have to bury anything there if we can get into a lava tube. So we've got our radiation, micrometeoroid, and macrometeoroid protection, as well as thermal protection already built. Geology's already done it for us. We just put an inflatable habitat in a lava tube. But then you've got the power issue because you've got to survive 14 Earth days of darkness and no solar power. So, well, NASA's made the decision in this architecture go round to use fission power on Mars. We could test it at the moon and go to a lava tube as a habitat rather than the South Pole, which is very difficult to get to in terms of just the orbital dynamics. So it's start small, have a foothold, and then we go to the poles. Once we've done the prospecting to show that we have water ice that has a very proven reserve potential.
Sounds complicated.
Well, I don't think it is, to be honest with you. I mean, it's these are the things that need to be considered, and I have the advantage of being able to look back on what I've learned because most of my life is behind me now, and connect those dots as I've gone through and learned these different disciplines. And if I can connect the dots, I think anybody should be able to connect the dots because hello geologist, it's to me it makes it's logic, but it's to being able to understand the different facets that you need to get to that logical conclusion. That's the bit that takes time.
So what happened throughout the years that we are the last Apollo mission, or the last anyone that was on the moon is in 1972, I believe, in December. Since then, we're in 2025. What happened along the way that this conclusion that is so obvious that you're making, why hasn't it been implemented?
All right. Before I get to that, I just want to finish the resources question. You said what are resources?
Sorry, yes.
All right. So
Sorry.
so you've got two basic categories. You've got resources for use in situ to support humans on the moon, resources for export. All right. So a lot of helium on the surface of the moon because there's no magnetic field and no atmosphere, so the solar wind bombards it, and there's a lot of helium. Helium is in great demand now, even in rocketry, because helium allows a constant flow of the cryogenic propellant to the engines, so you get constant thrust. But quantum computing, helium is very good for cooling quantum computers. They have to be down close to absolute zero in order to work most efficiently. So medical instruments, national security requires a lot of helium in their detectors. So there's a big market for helium, and we have very little helium on this planet. If we expand out to nuclear fusion technology, helium-3 is what I've called the nirvana of nuclear fusion, where you fuse two helium-3 nuclei and you end up with a helium-4 and 2 protons, or basically hydrogen atoms. So you've got no toxic byproducts, and you get an awful lot of energy. And the studies that have been done suggest that one shuttle cargo bay full of helium-3 would fuel the United States for 1 year. The problem we have, fusion technology is not a reality. Commercial fusion reactors are not a reality. But fusion technology, Korea and China are investing heavily in fusion technology. And they are now up to multiple minutes sustained fusion reactions. And they are pumping a lot of money into that type of research. And they're looking to the moon to get the fuel. And this is what some commercial companies in the United States are also doing. They see a potential for a market. Well, where do we go to get the helium-3? That's a resource that's a potential export back to Earth. Um, Another potential export, and this is something that the USGS is now starting to look at, is critical minerals. Can the moon solve this nation's critical mineral issues with rare earth metals, platinum group metals, and those sorts of things? And we know from science that there are areas enriched in rare earths on the lunar near side. We've got the orbital data, but very coarse grained. We've got a composition that is very ill defined, but it's much higher. And these are 60 kilometer per pixel data points. That is much higher than the highest rare earth element rich sample brought back ever from the moon. So we've got evidence again for lithologies on the lunar surface that we don't have examples of in the collection. So there are resources for use in situ and resources that could be for potential export. But it all comes back to actually understanding the reserve potential of each one of these resources. So does that I think that now answers the resource question, and you have to remind me of what the next question was because I've forgotten.
Before we get there, so what about water?
Water is for use in situ for life support, but rocket fuel. But it depends on the engine. Water is good for oxygen. Everybody needs an oxidizer for chemical propulsion. SpaceX has chosen methane. There's no methane on the moon. There's very little carbon. You have to bring that with you. Then you have to make it. Where Mars, they say, well, we can make methane on Mars, but there's no methane on Mars. It's very trace in the atmosphere. A lot of CO2, which means you have to split the CO2 and you have to split the water, then take the hydrogen, combine with the carbon from your CO2, and then you get methane. So there's a very complicated process. If you look at liquid oxygen hydrogen engines, all you have to do is split water and be able to store the cryogenics. And hydrogen is the issue because of zero boil off. It's a very small little piece that can get through gaps very, very easily. And so that's why people like the larger molecules, because they can be contained much better. But technology to sort of have zero boil off hydrogen storage needs to be invested in, as do, and liquid oxygen hydrogen gives you the most chemical propulsive bang, if you like, of any chemical engine that we know. And so you get a much better engine, but the problem is holding on to that hydrogen so that you can use it, because you're going to lose some. So part of the thing is, if you get water on the moon, you don't split it into oxygen and hydrogen until you actually need it. So you store the water, you don't store the hydrogen, and then you refill that way. But then again, that's technology developments are needed there in order to do it. So it has a lot of potential. Other things, so you got two end members to water use. You've got life support. You need to drink water, and you're going to stink, so you need to bathe occasionally. But then you've got, you can crack it and use the oxygen for breathable atmosphere, and then use the hydrogen again to maybe create more water. But the other end is chemical propulsion. In between, you've got a sort of a chasm of economic potential. Or do you? If you have habitats, you really need, as I said, a meter thick sheath of water around that habitat for ionizing radiation protection. Then you cover that bladder with 2 meters of regolith. You've now created a protective zone for humans to be able to exist, to be able to function, to be safe. So that could be one thing. There's also applications for grey water, right? So are we going to be able to come up with ideas of grey water cooling systems. I don't know, but it's going to take brighter people than me to figure that out.
But if I understood correctly, we know that there is water. We just don't know how much. And how much also depends on where you land.
Well,
And
we don't know how much. We don't know if we can access it. We don't know if we can extract it. And we don't know if we can refine it on the lunar surface. So there's a lot there's four things just there that are we need to know. So basically we need mobile surface assets on the moon to go explore and prospect to understand those things.
You mentioned about the in-situ resource utilization, and it sounds and you talked about inflatable habitats within the
Mm-hmm.
lava tube. From your experience, do you see this as a more better, higher possibility for that to happen sooner than, for example, using the ISRU to 3D print habitats? Because this is also something that's gaining traction as an idea. People are excited about it, but I think that there are real challenges to this, and an inflatable habitat would just be much easier. Except that it's the radiation issue. So
if you do it in a lava tube, it's not an issue. Right? You need a pressurized space, and if you were not in a lava tube, you'd have to cover it with regolith and a meter thick sheet of water. But if you're in a lava tube, and there's certainly more than 2 meters below the surface, you've got your protection. Everything we talked about, thermal, radiation, meteoroids, you've got your protection there. So to me, if we're going to start and get a foothold on the moon, you want to keep it simple. So you need a habitat. I mean, I keep seeing these NASA depictions of a tin can either on the surface or elevated above the surface of the moon. Well, that's just a killing box. So, okay, maybe you need to start there at the South Pole, or maybe you need to start in a lava tube to actually get the experience of living in the lunar environment. I mean, because the geology is actually giving you a head start. It's the same thing with resource utilization. Geology gives you a head start in processing because of all the impacts that's ground up the bedrock into regolith. So you don't have to do any crushing and grinding. You may have to do some sieving, but it simplifies the process. Because if you go to a hard rock mine anywhere, the biggest piece of equipment is the crushers and grinders that you get to crush your rock up so you can extract the material from it.
So speaking of the biology, do you think that there are lava tubes in locations where there is potential resource of water that can be extracted, or they're further apart that we need another challenge of getting the water to the lava tube and back and forth?
Well,
do we know about this or no?
We don't. Well, there are no lava tubes at the poles. Okay. All right. So they're not close to where the thermally shallow craters are. However, we now know from orbit, which came after samples brought back by Apollo, when it was shown to contain water, and the water was actually diffusing out of these little volcanic glass beads. So going back and looking at orbital data, we now see that these, what they call regional dark mantle deposits, which means big regional pyroclastic fire fountain deposits, they have a hydration signature. They're in a volcanically active area. We've now got more detailed maps of lava pits and lava tubes, and I haven't connected the dots between the water map of the pyroclastic deposits and where the pits are, but maybe we should be looking at these pyroclastic glasses that contain a water hydration signature about more than twice what we measured in the Apollo 17 and Apollo 15 glasses that were brought back, that we see from orbit. Maybe we should start there around a lava tube. For example, there is one, Aristarchus. There is a lava tube that extends from a rill, which is considered to be a collapsed lava tube, and you can see from the gravity data that there's a negative gravity anomaly and a long sinuous line extending to where that rill ends and the lava tube goes underground. And in Aristarchus there are a lot of pyroclastic deposits that contain a hydration signature. So how much water is in that hydration signature? We need to get to the surface and figure it out, because with those data, they are 280 by 280 meters per pixel, I believe. Maybe it's 240, but it's sizable. But we need to get to the surface and actually do some granular testing of the potential of these deposits to be used for, a water resource. And you've got a lava tube right there. So, if I wanted to go for a low-hanging fruit, maybe that's a place to look at as well. And then eventually go to the poles once we know exactly where to go.
So, based on what you're saying, there's lots of unknowns and known unknowns that we've accumulated throughout the years. And to go back to kind of the general overview of the previous conversation, how come the last mission was in 1972 and we're in 2025? Yep. What happened that we still have these as unknowns? Or at least... sorry. Yeah,
because we went to the moon in the 60s for the wrong reason. It was to beat the Soviet Union, and it was to deflect from policies down on this planet that weren't going very well. John Logston is a professor from George Washington University, wrote a book. I can't remember the title, but it's about the reason for Apollo. That's not the title, but it is. We start to see a snapshot of why we went to the moon, and we went in the spirit of international competition. So that's what I tell my students. We learn from history, otherwise we're destined to repeat it. We don't go back to the moon in international competition. That is not sustainable, because once you win the competition, now what are we going to do? So asking that question, and this is one of the fundamental things for the League United States Lunar Exploration Roadmap. When we started this roadmap, we started with the question, why? And that led us to our three themes, and it led us to the development. So we need to think about history again. Let's look at international cooperation. So the United States and the Soviet Union both returned samples, and the Soviets had 3 successful robotic sample returns, and there were 3 sample exchanges between the US and the Soviet Union, Apollo for Soviet lunar samples. And that started to build up trust. That led to the Apollo-Soyuz missions. That led to American astronauts on the Mir space station. That led to the International Space Station that has been permanently occupied for over 20 years by an international cadre of astronauts. So we have examples in recent history and history that's still being made with International Space Station. So we're now hearing we're in a competition with China, and I shiver. And I've actually broached this with those in higher places and said, hey, How about a sample exchange with China, Apollo 4, Chang'e 5 and 6? They said it led to good things with the Soviets and then eventually Russia. Have you thought about that? And no, they haven't thought about it, but it is being seriously considered. But the politics aren't right now. So hopefully it has gotten. I know it's progressed. It's got to the embassy in Beijing, but I don't think it's progressed any further than that. But this is something that we can learn from history to actually start creating cooperative agreements. Now, I really like the Artemis Accords because you've got 53 countries signed up to that. The only downside to that is what do they get out of it? And that's not been defined, and that's a mistake. But I think there's ways to get around that and make this happen, to bring them into the fold, so to speak. Because if you look at the Space Technology Mission Directorate's technology gaps, there are many and they are vast. That's a way for our international partners in the Artemis Accords to contribute to getting humans back to the moon to stay.
What you're saying ties up with the topic that I wanted to bring up, which is the paper that you wrote.
Oh yeah.
Before I get there, I just want to say that it's unfortunate that what you're saying actually, as like the sentiment of you want more collaboration, is shared by everyone, all the experts and scientists I've spoken to and with, and they genuinely wants to collaborate. They never see Russia, China, everyone as on a scientific human level wants to cooperate, and those policies seems to me that they're just politics. They're coming from a top-down approach, and it's unfortunate because the scientists established relationships, like you mentioned. It's the success of the International Space Station. Lots of scientists and astronauts are friends or colleagues,
Yep.
and they want to continue to collaborate.
Yep.
Correct me if I'm wrong, but I think Russia might be excluded from the Lunar Gateway.
Russia is absolutely excluded.
That's
I mean,
that is
they are
unfortunate.
still. It is unfortunate, but I call it science diplomacy,
Okay.
and it's to educate our decision makers on how science diplomacy got us to space station and how it can get us to the moon to stay. It's not the fact of beating China, it's the fact that we've got 53 nations signed up to the Artemis Accords. Now we need to use that to get us there. We all go together. And so I think that gives us an opportunity to really make a difference this time and to push this space policy into the next administration.
And this really shows the importance of the work that you've done when with the international collaboration for the lunar
Yeah.
the prospect campaign, uh, because it kind of ties back the community, like you
Mm-hmm.
said, of lawyers, experts, scientists, governmental agencies,
Mm-hmm.
or any agency that is involved, and it's the ecosystem that you create by this
Mm-hmm.
campaign. So,
Yeah.
would you like, please tell us more about it?
Well, you think about that, and you keep as soon as agencies hear campaign, they freak out because that's a lot of missions, and we can't afford that. So the interesting thing is that between now and the end of this decade, there are at least 30 missions to the moon that are funded and scheduled, and then there are at least over 15 that are under concept review waiting funding. So our thought was, why don't we just coordinate the missions that can help us do resource prospecting? So we've got LRO, of course, great data sets. Know the team very well. And so, of course, we can get pointed to the data sets that we need. That's brilliant. Um, we also had Lunar Trailblazer, which is unfortunate that it's not getting the data that's needed, but let's see if we can get it flown at some point in time with hopefully they've got an engineering spare. Excuse me. But Chandrayaan 2, the Indian mission, um, they have a very capable radar that will tell us about what is going on in the near surface regolith all over the moon. And they are now in the midst of doing a 2 meters per pixel mapping exercises of both lunar poles with radar. That is going to be really telling in terms of buried water ice in the poles, and also for buried boulders in the regolith when you're in the areas of quasi-permanent sunlight. So we know where there are few buried boulders, so we can move that regolith to bury a habitat and create a launch landing pad. So we just asked, would you be willing not to change what you're doing, but at least if we've got these targets, can you point us in the direction of your data files so we can go look at them? Sure. Yeah, the Korean Pathfinder Lunar Orbiter, same thing. I mean, they've got the American instrument ShadowCam. They've taken pictures of the permanently shadowed craters that we want to go look at. We've got access to them. We can map out traversability into these smaller ones rather than the large ones, which I think are going to be much more accessible. But then what KPLO has as a very wide view of both poles with their gamma and neutron detectors, and the North Pole looks as if it's got more water in it than the South. So it looks like there is more, but that to me is the beauty of it. And then we get the Canadian lunar rover. You're going to go to the poles. Can you give us? We would like the data that you get with regards to the subsurface at the poles with regards to volatiles. Are you going into a Viper? Viper is still alive. Viper is not dead. Viper is going to be the first mission to go into a small PSR and test the validity of a cold trap, and that's going to be pivotal because, and the Lupex, the Lunar Polar Explorer from China, from India and Japan, another rover at the South Pole looking for volatiles. We've asked them, would you be willing to give us your data so we can build predictive models, prospectivity maps, if you like, of water ice at the South Pole? Sure. So it's coordinating existing missions, at least initially, so that we can build integrated data products to show where the next landed mission needs to go, and really test whether or not we have, or test the reserve potential of what we see from the orbital data. And that we're not designing any new missions. We're using existing missions. And again, this is something that we need. And what it's going to do, it may not show us exactly where the richest deposit is, but it will tell us where we need to go on the surface to test out these hypotheses. You bring those data back into those predictive products and you refine them. They get better, they get better, they get better. So on and so forth.
It's not just the sharing of the information, it's having more eyes looking into the same data. It's just much more, if you want to review anything, you need more eyes on it to kind of parse and analyze.
There's more eyes on it, but it's a combination of different data sets. Mm-hmm. So you get a fully integrated surface and subsurface potential for water ice. That's what we look. See, radar and neutrons give you subsurface. You've got your infrared spectra and laser. The laser reflections are what tell us that told us there was frost there. ShadowCam doesn't see frost. So we really need to ground truth that, because we've got a dichotomy. So there are some things that really need to be, we really need to get to the surface. But with these integrated data sets, this is a way to start bringing ISRU into the critical path for human exploration.
How is the data between the different collaborative entities, collaborating entities will be shared? Is it through papers, scientific publication? Is it going to be classified?
It's going to be through their data systems. They're all
Okay.
government run, so
Okay.
they're all government run, and we assume, and well, they are. All their data is free.
Okay.
We just need to know which data sets to look at
Mm.
and then be able to extract them. We need to know what geodetic frame of reference they're using so we can put them all on the same geodetic frame. And then those overlay of those data sets is what is going to give us that integrated approach.
And do you think the AI would have a?
Oh, I'm sure it would. AI is the solution to everything now, a bit like Starship and going to the moon. So, but I don't know how good AI would be. As I say, as a man that has more of his life behind him than in front of him, I'm a bit skeptical of it at the moment. But that's
Yeah.
because I don't fully understand it. So I have something else to learn. So and I will certainly learn it. But I think there's certainly potential there for having that come into play. But again, like everything else, you would generate a model, whether it's AI or not. That model then has to be tested.
The last question I have,
Mm-hmm.
or what's your advice for the next generation of space exploration astronauts, or even the private companies who are involved in the space or governmental agency? What is this one thing that they have to be aware of um, in order to fulfill a realistic dream of actually space exploration?
Mm. Well, as we've seen from the initial CLIPS landers, the space is hard. It is, if you got humans in the loop, it's toxic. So that we do know, but it's a multidisciplinary subject, and becoming, for example, in my case, becoming very geologically knowledgeable is good, but it's about 10% of what you need to know. And I would say that for young folks, an interdisciplinary education that covers the different aspects of that I pointed out, where you've got geology, you've got engineering, you've got business, you've got policy, you've got politics, you've got ethics. That's you need all of that to actually craft an architecture that is going to make life better down here as we go out there. And I'm trying to convince our university or my university here to become multidisciplinary. So we're putting together a space exploration minor that covers 3 colleges, and it's caused a few voices of concern of how are we going to manage this? Who owns it? Well, the university owns it. But no, which college? Well, all 3 of them do. But how are you going to administer it? Well, here's the administration plan. This is how we're going to do it. What's the product? Well, it's to get these kids into the space sector. So we have a commercial advisory board that will tell us what we need to have in our curriculum so that they can come out of Notre Dame and be productive on day one. So that's how we're going to do it. But the only constant is change, and if you're not willing to change, then we have to move on, I think. But so that would be my advice: is a multidisciplinary aspect, and everything that you do, you may not think is relevant right now to your career, but it may be one day, and you better pay attention now so that you're not left lacking in the future.
Thank you. That's a great note to end the conversation. I am really grateful for your time. Thank you so much. I really appreciate it.
No, thank you, Tara. I've thoroughly enjoyed it. And as I say, my favorite subject. So
thank you. And I hope that with any new findings or anything, I would be very happy if we can do this again with new information. Thank you so much.
Very good. Very good. No, thank you. And for those who are listening, thank you for listening. So.